All right, guys, let's get started. Oh, sorry, let me connect that. All right, there we go. So we got the screen in the background. Let's start with week 2, okay, today. So let's go to Brightspace. Materials owner, content. So I think we started the first lab last week, and I believe we did 3 of the 4 problems, right? So I have one more problem to finish, which is corrupting the cipher, right? Corrupting one bit of it. So we'll do that today. So I'm going to break today like in half. Second half will be just solving that problem, right? Going over that. And then during the first half, I'll do the lecture for today, just introducing some of the topics in more detail. Yeah, so this should be recording. Wait. Yeah, it's recording there, right? So, okay. All right, and then on Thursday, we will do a problem, right? So remember I said we're going to do one very simple substitution cipher, and really it's to kind of get everyone, it's just really about like practicing Python a little bit of background, etc. All right, and that will be the whole assignment. So we'll code it from scratch, and we'll practice, and that will be your assignment. So let's take a look at Brightspace here. So this is what we started last week, the secret key encryption. Okay, so we went over all these materials, and I've added already the link, so you can start submitting your assignment there, and then we'll finish this up. I'll get on the VM during the second half of today, and we'll go over that. And then, as I said on Thursday, the focus will be on this. I will kind of demo and just describe the problem, you know, what I want to do, and just to show you that you can create your own ciphers, obviously. Probably not, they're not secure. You should know that, regardless of how difficult it seems that they are to code, or how much they, if they're not based on solid principles, they're going to be very insecure. All right, but we'll cover that one. I usually like to cover that one to just get everyone to code in Python, and so that they get comfortable. Okay. Okay. All right. So yeah, so please sign in also. Pass this around. Okay, so the topic today, so today we're starting formally to get into cryptography. Okay, so this is a formal introduction. Now, so I'll use the whiteboard for this, as I like to lay things out, but we'll lay a lot of the foundation for secret key encryption. I want to say, okay. All right, so I'm going to stop, and I'm going to need to use the whiteboard. Okay. And basically, we're going to start talking about something called the crypto primitives. Okay. And it's, one good analogy is think of this as Legos, right? So I'm giving you some blocks, and these are going to be the building blocks that will allow us to create very complex ciphers. All right. So your goal will be to get to SSL, for instance, to understand how SSL works, but it's going to take a lot of time for us to really, lay the groundwork, these primitives that will allow you to truly understand how SSL works. Got it? All right. So, and you may not believe me that it would take many weeks to really understand SSL, but it does. Okay. All right. So, so before I start, I guess I should have asked, do you guys have any questions about anything? Everyone good? All right, great. So, yeah, so thankfully, my pencil works. Let me change to red. All right, so yeah, we're going to talk about cryptography. And so crypto, right? So, take notes, right? I should say this is really important. So cryptography, as you know, is everywhere. Um, just kind of everywhere, right? So, in all your network communications, everything on email, Brightspace, Amazon, everything. Okay, so we know that. So let's start with what is a secure communication. So, usually, as you will do with a lot of the assignments, you'll be working with a partner. And even in our examples, we will use the case of Alice and Bob, right? So usually the communication happens between two parties. Now, these can be automated, obviously. They can be like two systems talking to each other for some reason. But to keep the example simple, we're always going to be talking about Alice and Bob. Okay, so Bob and Alice. So let's do Bob, and Alice. Okay, so two parties. So the classic example is the web server e-commerce, communication where you have client server architecture, right? So you have a client, okay, and then you have a server. Okay. So you want to establish communication between the two parties, right? Something such as SSL, secure socket layer. All right. So we're going to talk about the principles, and the goals of this are to have a communication that has no eavesdropping, confidentiality, and no tampering, integrity. Right. So remember, so these are the two goals that we're going to be looking at right now in the communication. Okay, so let me. So basically, secure socket layers is a protocol to secure web traffic, and there are two main parts, okay, for SSL. SSL will have two main parts. This whiteboard used to work really well, but they changed it, and it doesn't write as well. All right, so basically, there's going to be the key exchange first. Key exchange. So we're going to exchange the key or share the key. Share the key, right? And then we're going to have, once you've shared the key, the actual communication. Okay, so this is called, I don't know why it's very not easy to write on this. Just give me a second. See if I can find another whiteboard. Okay, this one seems a little bit different. Yeah, thank you. All right. Okay, so as I was saying, so in secure socket layer, we're going to have two steps, right? One is going to be the key exchange, and then once we've exchanged the key, the actual communication using that key. So we are going to share the secret key. Secret key. And that's going to happen with something called PKI, the public key infrastructure. okay, which is one of the topics that we will talk about later. And then once we've exchanged the key, then we're going to use that key to actually do the communication, to transmit the data. So transmit data with, with a shared key. With shared key. All right, so this is pretty important, and it's one of the topics that we were discussing last week. All right, so all we were doing is we were transmitting the data with a shared key, but we haven't really figured out how to exchange the key. All right, so that's the basic idea. So SSL is the protocol to secure web traffic, and there are two main parts. One is called the handshake protocol to establish shared secret key using public key cryptography, and then the second part called the record layer, transmit the data using a shared secret key. Okay. So now we're going to establish for symmetric encryption, what process we can follow. Okay, so let me add another. What are these? Presentation. What is this? This screen used to be different. Do you guys know how to change it to the old version? Anyone know? It used to be a white, really nice screen, and they changed it on me. Just feels different. Okay. All right. I don't like it.
Is it the next to recording? Is it
Which one?
next to recording at the very top?
View. It used to have, do you guys remember? It used to be just a white screen, right? And like a PowerPoint and maybe full screen. No, this doesn't write so well.
Would it be the three dots at the bottom?
3 dots?
Yeah, if you go to the left at the bottom in the sidebar. Sidebar, yeah.
Here. Mhm.
Or on the three buttons on the bottom, right on the screen. Sidebar.
Where?
On the very bottom, this is whiteboards, apps, and the black bar on the bottom. At the very bottom.
You mean here? Oh, here.
Yeah, follow on the right.
To the right?
This is the
Yeah.
Yeah,
I don't know. I know this used to be different, and I've never had. I mean, you guys have taken classes with me. I always use that, but this just feels odd. Okay, well, I guess I'll have to figure out later. Right. Let's create a new screen. All right. So anyway, so symmetric encryption, right? So we're going to talk about what we were discussing before, block ciphers. Nope. Block cipher. So symmetric encryption. Metric. Symmetric encryption. It's like not. All right. All right. So how do you basically, what's the process here, right? So we're going to have several parameters that we need to consider. We have the plain text message, M. We're going to have the key, K. We're going to have an encryption algorithm. We're going to have a decryption algorithm, okay? And we're going to have to use all of these together to establish, produce a cipher and communicate securely. So the process then is going to start with M, okay? So think of Alice sending the information, okay? So this message will need to go through an encryption function. Okay. Like that. Okay. This encryption function will take in as input also the key. K. All right. So then the encryption function is the algorithm itself. So think of E as a function. It will take in K, comma, M to produce C, which is the cipher. Okay, this is what we are encrypting, basically. Okay, this will be transmitted and will be received by Bob. And then Bob will have a corresponding decryption algorithm. Okay, so which will also take in as input the key. Do you see that? So then now you will use the decryption algorithm with the same key. It'll take in the C cipher and it will use this to produce M. Does that make sense? So this is the overall architecture, if you will, of symmetric encryption. Okay. So basically here, obviously we have to get into the definition of E and D, and that can vary, but this is just initially how you can, the overall definition of the process. Okay. Any questions? So here, what is K? K is the secret key. All right. M is the plain text message. And these two are the algorithms. And I guess I should mention that C is the cipher. For most of the semester, we will be using this notation to define the encryption. Okay, just like that. Any questions? All right. So, so the encryption algorithm now, so here's a few things that you should be aware of. The encryption algorithm and the decryption algorithm are publicly known, right? So there's no secret about them, all right? It's not like you're keeping it a secret or anything like that. So E is the encryption algorithm, D is the decryption algorithm, and the only secret is K, which is the key, okay? It's the only thing that you're going to keep a secret. All right, so these algorithms can be very involved, but at the end of the day, they have one operation that is very important and is the next thing that we're going to look at. This operation is the XOR operation, right? So today I'm going to introduce that. You guys already know how to do it. And then throughout the semester, we'll be using it as one of the key operations that happens in our algorithms. All right, and I'll motivate a little bit why we use XOR. All right, so I need to click on this. All right, we're going to add page. Okay, we're in a new page. Okay, all right, so XOR operation. So XOR, of course, is really important. You guys have learned this when you learned programming and Boolean logic. So it has to do with the truth tables, okay? So basically, I'll just give you an example of how the operation works, okay? And then we'll take some bits and XOR them, okay? And that'll be it. So the idea with the XOR table is that one or the other, but not both, right? That's probably something that you learned, and that's really what we'll be doing. So, you have zeros and ones, right? So if you have 0, 0, 0, 1, you have 1, 0. See, there's a little lag, if you see that, which this used to be very responsive before. All right, so we're going to do these truth tables here. So 0, 0 should be, for the XOR operation, should be false. Yeah, so 0 or 1. 0. Yeah, 0. Okay, good. And then 0, 1, 1. 1, 0, 1. 1, 1, 0. Do you see that? That's all you have to know. Like, write it down in your cheat sheet or something. And this is basically what you'll be doing. On the exam, I'll give you some little problems like that, etc. But this is the operation and encryption, believe it or not. Now, why do you think this is a key operation in cryptography? You have to think of when cryptography was invented, right? So it was invented a long time ago in the 70s and before that. You're encrypting a lot of data usually. So why this operation? Because this is an efficient operation in the computer. Computers are binary, as you know, and you have logic circuits, right? And these logic circuits natively do operations of bits. Do you guys understand that? That's key because throughout, cryptography, performance is always really important. All right. You want elaborate algorithms, but you also want really fast algorithms. Okay. And so this is a key thing to understand, that regardless of how you're looking at blocks of data, your text, your numbers, whatever it is, your movie, your Netflix movie, everything is being converted to bits, and everything then you're doing these operations to obtain, I have 2 bits, 0, 0, and I obtain another. Okay, so the underlying operation is XOR. And this is basically what you guys know as the truth table. So let's do an example of how this would work. So let's think of a plain text message, right? So we're going to think of how you do things in cryptography. So I'm going to have my plain text file, or sorry, message, my plain text message. I'm going to have my key, and then I'm going to have the cipher, okay? So we're going to take a look at this. Okay, so plain text is going to be just a byte of data, so some bits. So I'm going to do 1, 0, 1, 1, 1, 1, 0, 1. You see that? So that's my plain text message. So of course, this was a message of some kind, a sentence, a paragraph. You use the ASCII table and you converted this into bits. Okay. Then you're going to have a key, and you want a key that's, a random sequence, right? So you randomly initialize a key of random bits, and that's what you're going to use for the encryption. All right. So the key in this case is going to be 0, 0, 1, 1, 0, 0, 1, 0. Okay, like that. That was a 0 for my example. All right. So now what you need to do to produce the cipher, what is the cipher here? The cipher is literally the encrypted message. That's it. You see that, guys? So that's basically it. So now you proceed using this logic here of the truth table to produce your cipher. And that's the native operation or native primitive operation of cryptography. Okay? AES, DES, they all use this. Okay? So that's the whole point. But we're going to see some problems, right? Not with this operation, but with the complexity of it that require us to, use more elaborate algorithms. And within those algorithms, we will still use the XOR. But we just have to add more complexity in a sense to achieve a little bit more security. All right, so let's do this operation now. So this should be, oops, try to do a line here. Oh, I did a line. All right. So 1, 0, 0, 0. Oops, that's a terrible. So 0, that's a better one, right? So I'm just using these truth tables. So 1, 1, 0, 1, 1, 0, 0, 0 is 0. And then over here, these should be 1, 1, 1, 1, right? Do you guys see that? That's it. That's an XOR operation. Okay. And then from here, then, yeah, we got a plain text, a key, and then we have a cipher, and then you would send this out, as secure communication. Okay. So we did that. And that should be pretty simple. All right. So, So what is a cipher then? So as we start to talk about symmetric key encryption, you know, we want to start to define what a cipher is and what is a secure cipher also. So those are actually two important things that we're going to try to establish today. All right, what is a cipher and what is a secure cipher? So let's add a new page. Okay, I'm going to close this one. All right, so symmetric ciphers in this case. So what is a cipher first? Cipher, what is it? So a cipher is defined as a pair of efficient algorithms E and D. That's basically what a cipher is. Okay, so the encryption function and the decryption function. Okay, so that's basically a cipher. So that where, so we want to where, so where we have that, you know, given a K and an M, K comma M, K comma M, we have our cipher, all right? And given that we have, and I'll say here, and given that we have D, K, C, we, you know, obtain the equivalent M, okay? So that's basically the definition of a cipher. We have a couple of functions as defined as a pair of efficient algorithms, E and D, where E, K, comma, M equals C, and D, K, this should be C, C equal M. Pretty simple, right? Pretty straightforward. Obviously, this has to have has to follow the consistency equation, which basically means the following. So if you have D, K, comma, E, K, comma, M equals M. Do you guys agree, right? All right, so you know here that EKM gives you the cipher, and then K cipher of D gives you M. All right, so this is called a consistency equation. So a cipher is defined in this way, okay? It needs to have this relationship that you always get your M. It can't vary, right? It has to be always like this. You always want to get that Netflix movie every time, right? So it can't vary. Any questions? Pretty simple, right? Pretty straightforward. So, all right. So that's the definition of a cipher. So E is often randomized. So you'll have some bytes to perform the encryption. And that's, you know, basically the idea. All right, so now that we know the definition of a cipher, which should be straightforward, we want to answer the question, what is a secure cipher? Like, how do you really answer that question? Have you ever thought about that, right? So how do you say that something is actually secure? Before we get into it, let's say that somebody asked you, how do you define that something is secure?
Cipher wise.
I mean, yeah, or anything. How do you say that's secure? You know, think about it.
Ensure that wherever you want to secure access, like people to access it.
Okay. But how do you define it? How do you define that something is secure? That, you know, what's the definition of a secure cipher? It's a little bit more complex than we think, actually. You know, how do you actually know? Yeah, this is secure. Usually we have to quantify things, right? We have to say something like this is 100% secure. Do you guys see that? We can't just like qualitatively define something. We have to, you know, in some measurable way, say how secure it is. So then how do you do that? How do you define that a cipher is secure? Or what makes a good cipher? What do you guys think? I mean, I'll give you what someone said is the definition, but
if you're able to run it through like a programming.
okay. That's a good, yeah, like if you run it a million times, right? And out of those million times you never broke it or something like that, right? So yeah, so that's a good way of thinking about it. All right, so we're going to start getting into that, and we're going to look at what Claude Shannon say of what is a good cipher. All right, so he provided a way of defining a good cipher. So let's start with one example. So there's something called the one-time pad or OTP. So we'll start there. Okay. So we'll start with something called, example of a secure cipher, right? So we'll start with OTP, which stands for the one-time pad. This is the one-time pad. Okay, so basically, this is a technique from, in the beginning, like 1917. Basically, what this said is you had a random sequence of bits as long as the message. That's where you start with the example. Like if you're starting to think about how to, what is a secure cipher, people like Claude Shannon just say, let's just start with the simplest thing. We have XOR, which I just introduced, right? And I did it for a very small block. But Claude Shannon takes it a step further for the one-time pad. So you're just padding it one time, right? That's the idea. So and so then you define this problem as you have a key, and that's really the whole trick to it. You have a key of a random sequence of bits as long as the message. So, random okay, random sequence of bits It's a random sequence of bits as long as the message. So this is key. As long as the message. All right, so that's the key in the one-time pad. So that's the one thing you guys have to remember, right? So the random sequence of bits as long as the message. So then all you have to do to obtain, because we already know what a cipher is, right? So if I want to obtain the cipher, given our definition, I'm just going to do C equal E K, right? M, regardless of what we need to define what this algorithm is going to be, right? So we don't know yet. And that's what I'm about to do also in the one-time pad. Okay, so there's two things that I'm adding here. One, the key is as long as the message. And then what is the algorithm? So now I'm going to define the algorithm to be K XOR. So this should be the symbol for XOR. Okay, and then M. Do you guys understand? So we defined a cipher before. Now the one-time pad, we basically add two new components to it. I think I can go back to previous ones. Can we? So we defined, yeah. So we've defined these functions, right? So this was a cipher. These were, that was a cipher, right? So we were just looking at this. So what is a cipher? E and D, and then we have this relationship. Okay, now we look at our very first cipher, which is going to be the one-time pad. Okay, there we go. And I'm just going to say, okay, I'm going to say that the key is a random sequence of bits as long as the message, and then E is just XORing K with M. That's it. Got it? Pretty simple. So this is the XOR operation. And so now we want to ask the question. All right, we're XORing, we have a random sequence. And now I should, I took my time writing this out because we're going to like break, we're going to look at every single word in this statement and kind of try to understand it. So one really important thing, and you have to be careful, is random. Like if I wrote on the exam something like a sequence of bits as long as the message, that's not entirely true. That's not going to make it secure, right? It's got to be a random sequence of bits as long as the message. Obtaining random numbers is actually really difficult, okay? So in cryptography, one whole section of study is just that. Can you get random numbers, first of all, from computers? What do you guys know about computers and random numbers? You guys have heard that computers are what? Deterministic or random? What have you heard? I'm sure in some class, somebody said computers are, if I say multiple choice or two choices, computers are deterministic or random, what would you say? Deterministic, right? So your algorithms are deterministic. What that means is that you give it A, you're going to get B all the time. Do you see that? So how do you obtain random numbers in a computer? Well, there should be an algorithm, right? You go to Python or something like that, and Python runs through an algorithm and it gives you a random number. So is that random number that you get from Python random? What do you think? Do you understand my question? So I just said computers use algorithms. The algorithms are deterministic. Then you go ahead and you use an algorithm to generate a random number, and it gives you a random number. It's still not random. Why? Why? Because the algorithm is deterministic, right? And even if you throw in some bits in there that you try to randomize in some way, right? Where are those bits coming from? From some other algorithm that generated those. And that algorithm is deterministic. So at the end of the day, the point is that maybe you get random numbers that are not entirely random. Do you see what I'm saying? So you keep trying to do things to make them more random, but computers are deterministic. So in fact, what we're going to learn is that we use something called pseudo-random numbers. Okay, that's going to be actually the terminology. And we're going to explore some functions, and that's an important aspect of cryptography, because as we are starting to look at the definition of what makes a secure cipher, one of the key elements is that it should be a random sequence of bits. If it is not, if it's pseudo-random, then it is questionable that it is 100% secure. Do you see where I'm going with that? Now, don't misunderstand me. Sometimes that may be enough. And that's actually the key thing to understand. We make compromises in cryptography with performance, with random numbers. Does that make sense? So for instance, they use like physics and quantum computing and things like that actually just to create random numbers. Because supposedly, and I'm not a physicist, but supposedly physics is very random, right? The particles and everything are very random. So if you can use some machine to measure that, then it can create random numbers. Do you see that? And why is that important? Well, because if you require something to have a very random key, then you want to use something like quantum computing or something like that to generate that sequence for you. Otherwise, if you're just relying on Python and our very great algorithms in our libraries in Python, you get numbers that are pseudo-random. And we'll talk about pseudo-random number generators. What is pseudo-random generators? PRGs. PRGs. All right, so we'll talk about that a little bit later. All right, anyway, so that's one important aspect. Just keep that in the back of your mind, okay, as we start to define a cipher and how that works, okay? Remember, we are just looking at the one-time pad right now, OTP, and this is kind of the analysis. We're just trying to define what makes a secure cipher. So the question that we might begin to ask here is, so is the one-time pad OTP secure? Okay, we know that it's a random sequence of bits as long as the message, and basically then that key is this, right? K is, and then the message is here, and then you XOR it. Okay, that's what we are analyzing. So that actually takes us to a very profound question, very important one. What is a good cipher, right? So, another way of looking at it is what makes a cipher secure. So now I'll just give you a little bit of the history. So this was actually like solved or first proposed by Claude Shannon, have you guys heard of Claude Shannon? Rings a bell. You should know about Claude Shannon. All right, so very interesting character. He was a genius. He invented information theory. He coined the bit. You know how you guys we all say bits and gigabytes and all that stuff. He actually coined that term, and he was one of the first people to measure information, in bits and all that. So that's information theory, which is a science established by Claude Shannon around 1949. He was a genius at Bell Labs, became bored with that and invented cryptography, so that kind of a genius, right? Anyway, so yeah, he's really great. So anyway, so he's actually the first one to propose a solution to actually give us a quantifiable way of thinking and defining what is a secure cipher, okay? And he was just looking at this problem. So the basic idea that he came up with is the following. The cipher text should reveal no information about the plaintext. Okay, he was looking at it from the point of view of an attacker, right? So we have Bob and Alice trying to communicate, and then there's like Zelda, someone else. And if Zelda captures the cipher, because this can happen, right? Think of, you're sending your secrets, so somebody's going to try to steal it, right? So if you say right now, you like broadcast, I'm putting all my credit card information, my bank accounts and passwords here in this file, and I'm sending it across the internet. And everyone hears it, believe it or not, but a lot of hackers are going to try to steal your data, right? That's going to happen. I mean, you broadcast it, people are going to try to steal it, right? So that's how you have to think about this problem. What if you encrypt it and someone intercepts that cipher? Do you see what I'm saying? So then that's how Claude Shannon starts to think about this problem. So he says the basic idea is the cipher text, which is C, right? C here, should reveal no information about the plain text, M. Okay? That's the basic idea that we want to think about. Okay, so Claude Shannon wrote a paper where he analyzed the security of the one-time pad. And then he basically proposed a definition, okay, which I'll give you right now. So this is the definition of what makes a secure cipher by Claude Shannon. And this is what a lot of people use as the foundation to define all ciphers, okay? So we'll think about it. It's not it's like a math thing, but it's not an algebraic thing. Instead of you have to interpret it, and I'll show you how to interpret it, okay? So Shannon basically came up with the following definition for a secure cipher. So I'll just say here, definition right, for a secure cipher. For a secure cipher. All right, so and I'll just write the equation first, and then we'll start like dissecting it and trying to interpret it. All right, so basically, he wrote the following. PR stands for probability. All right, so you know how I asked you initially, how do we define something that's secure? And you said, run it 1,000,000 times. And so you're trying to quantify it, right? So this is what he proposed based on probabilities, okay? So he basically said the following. And I'll let you guys then tell me what you think this means. I'll just write it out and you guys can tell me. All right, so you know this notation already. So this is E, K, comma, M, this is a 0, M0, okay, equal C. And then you're going to say that this is equal, right? So that's the equal sign to probability, PR, of the following. Comma. Now this is a 1, not a 0. 1 equal C. And that's it. That is the definition by Claude Shannon as he was looking at the one-time pad, which is the simplest example that we can think of. So we know what E is, right? You guys already know what E is. What is E? Just the XOR of K and M1. That's it. And the assumption is that K is as long as M here. So M is what? The plain text message. K is the key, and C is the cipher. Got it? So what do you think this means? And as I said, this is the definition of a secure cipher. What is this? What does this mean?
The probability that the message, even with multiple different messages, it will send across all of them.
Mm-hmm. Okay, you're getting there. I think you're right. You just, yeah, say it again.
So
say it in another, say the same idea in another way.
So let's say I have message 1 and message 2, the same cipher. The probability of both of them being decrypted is the same.
Yeah, I think so it's you're going from M to C. Remember that we said that Claude Shannon thought the basic idea is the cipher text should reveal no information about the plain text. So go the other way around. Start from the C to the M's and say for a third time what you're thinking.
Okay, so you start with the cipher.
Yeah.
And then if you're going to try to find the original message,
yeah,
the probability of
yes, there you go. That's it. Nice. That's exactly right. That is, do you guys understand? And I'll write it down, but that's the definition, according to Claude Shannon, of a secure cipher. That's really important because the assumption is someone can capture your cipher, but your cipher should not reveal anything about the original message. We broke that rule last week, didn't we? Do you guys remember how we broke that rule? Remember the image example? That broke that rule because in the image example, I encrypted the image. So that basically means I grabbed that C, I looked at it, and what was I able to do? I was able from that to tell what the message looked like. Do you see what I'm saying? Whereas in the other example, when we use CBC, I grabbed it and I couldn't tell anything about the original one. So that one was more secure based on the definition of a secure cipher. Make sense? That's it. Any questions on that? That's a key fundamental concept for defining this, okay? So very good. So I'll just summarize, and if you have questions, raise your hand. So Shannon came up with the definition of the cipher. And that, and that basically means that the cipher has perfect secrecy if it meets this condition. Okay, it has to meet this condition. Sorry. So this means, given the ciphertext, as you said, you cannot tell if message is M0 or M1. You can't really say like, well, I look at C, and even if, let's say you're like, oh, there's a 49% probability that it's M0 and a 51 probability that it's M1, right? So at that point, it doesn't meet the condition because now you can use that information. You see that? You can start now just with that to say, oh, I'm going to go with M1 and see what happens. And you shouldn't be able to do that. It should be equal probability based. Okay? All right, another way of stating it. So the probability is the same. So if you're an attacker and you intercept a particular ciphertext C, then in reality, the probability that the decryption of C is M0 is exactly the same as the probability that the decryption will give you M1. Okay? All right, so hopefully that makes sense. So you have no idea, given C, whether it's M0 or M1, it could be either one. All right, and that's basically the definition of a secure cipher. So hopefully that makes sense. Raise your hand if you have any questions, but otherwise we'll move on to the next concept. Okay, all right, so now let's move on. So then basically we were talking about the one-time pad, OTP. Okay, so I'm gonna go back to one of these slides. This one, right? So we were talking about this one, okay? And Claude Shannon then analyzed this technique, and he concluded the following. So as long as the key is random, and it has to be truly random, then the OTP can achieve perfect secrecy. So that was the conclusion. OTP has perfect secrecy, perfect secrecy. Okay? So then you might say, all right, it has perfect secrecy. All I have to do is create a random sequence of bits. That's it. But what's the problem with that? What's the problem with the one? Why do we need to have other algorithms and not just use the one-time pad? If Claude Shannon assumed that the one-time pad, this technique that I just defined, has perfect secrecy, why can't we use it? Let's see if you guys... This is important, right? Because this leads us to the next set of algorithms. We can't, in some cases, you may be able to use the one-time pad, and that's great. Just use XOR, have a key, which is random sequence of bits, but it has to be as long as the message. What's the problem with that in the modern world? It's because of the length of the message. Exactly. Again, performance. What? 1917 is when they did this analysis. Yes, exactly. But even then, it was a problem, right? No computers back then. Or what is it? Those glass tube things that they use. So what's the problem? Well, this implies that if you can have a pattern of the key in the encryption. Right? Hopefully that makes sense, right? That's what this is saying, is that you can't let's say you're encrypting a whole movie, right? So how long is a whole movie? Take a whole movie and convert that into a sequence of bits. How long do you think that would be? That's a lot of zeros and ones, right? Now, create a key as long as that. That's what the one-time pad is suggesting that you do. So there's several problems with that. One of them is that you would have to send that key to your friend across the world, right? So think about that. So now, instead of downloading the whole movie, first they have to download the whole key. So it's like downloading 2 movies. Imagine if the whole internet was like that. So basically, we would double the amount of information that we have to send, right? Do you see that point, guys? That it would be like, it's almost like 2 internets. in terms of data, because one just for the keys and one for the actual information. So the problem with that is that it's not practical, okay? So we have to start making some compromises, okay? And that's going to lead in to block ciphers, the first example that we're going to use, because we are going to perform the same operation, but the key cannot be as long as the message, okay? So as I said, Claude Shannon concluded that this can achieve perfect secrecy, okay? But he also proved that to have perfect secrecy, and this is key, to have perfect secrecy, the length of the key needs to be greater than or equal to the length of the message. And that is just not efficient, okay? And basically what he's getting at, the point is that, you know, you'd have to, if you start repeating the key in there, right, to encrypt blocks, then you may start to add a pattern, if that makes sense. And that's the problem. There can't be a pattern in there. Do you see the difference? So maybe let's do an example here, right? So I'm gonna go in here. I'm gonna add a new page. Okay, so a random sequence of bits. Okay, so I have, let's say I have this, and this is my message, right? So this is my message. This is my message. So movie, something that I'm sending, right? So you have two options, basically A or B. And the operation, the underlying operation is XOR. So one is the one-time pad, OTP key. And in the one-time pad, we say that the key needs to be as long as the message. Just going to do it like that. All right, so that's basically the key of the one-time pad. Now, we assure security because the whole sequence is random from the get-go. You see what I'm saying? Like the whole sequence is random. Whereas, but the problem is, and this achieves perfect secrecy, but it's just not practical. So then we have to make a compromise where we introduce shorter keys, right, of a certain size. These are the blocks. So what that implies is, because this is not practical, we have to use shorter keys, which means we have to do several things. One of them is we will have to break the message into blocks of equal size. These are meant to be equal size. And then the last one, because you don't have enough information to fill the block, what do? You add padding. We saw that last week. Do you guys understand? Now, the rule still holds. This sequence here, this shorter sequence, needs to be a sequence of random bits. Really important. But what's the problem with this? Once you start reusing this, because now think about it, it's the same key, right? Same key and so on. You start adding, even though the blocks themselves, like the individual key is random, once you start using that throughout the message, you may start to add a pattern. Does that make sense, guys? You see that? So that's, so this is why then we can't just, that's the problem, right? So this is secure. This is not guaranteed. All I can tell you right now is this is not guaranteed to be secure. And I've already shown you an example of this with ECB, which we did also, last week, the electronic code book. So that's the next thing I'm going to show you, why, even though that block was a random sequence of bits, because now we're using it throughout the message, it's not 100%, we can't achieve the security that we would have with the one-time pad. Does that make sense? Any questions about this idea? Yeah, go ahead, please.
So if you're able to decipher a block of a message and you decipher, you just gotta repeat it through.
If you can figure out which part, the cipher, the key, or the message?
B.
Yeah, B. Okay, B is the key right now.
So if you're able, because you're saying it's repeated the whole message, but
It might be, yeah.
so if you're able to figure out one segment of it because it's the same.
Ah, yes. Okay, I think I get you. So if I figure out this, so let me see if I can state it in another way here. So I'm gonna do the following. I have a message here. What's the most common letter in the alphabet?
E.
E. And then an uncommon one is X, let's say. Right? Imagine, yeah, something like this is a frequency of things. So this would be a big message. But there's going to be a lot of E's because it's the most frequent, right? And then there might be another, let's say R is infrequent. Okay, so we have something like that. Then we have the key block. Key block. Now, I guarantee you that key, imagine it's a sequence of bits, is random, guaranteed. But what's going to happen when you always XOR these, right? So, and imagine these letters are converted to bits also. You see that? So what's going to happen here? Imagine that the cipher equivalent of encrypt, because this is the plain text message, M, this is the key, and this is the cipher, right? So what would happen here is, for whatever reason, that's the cipher. What can you expect this to be the cipher? So what would be the cipher of, if E is E and they're the same, and this is K and this is the same, then you can expect this cipher to also be 101. Do you see that? And what about this one? It would also be 101. Now this one might be something else. It'll be like 111, and then this one would be, I don't know, 000 for whatever reason. So even though the block itself of bits is random, because you start using it in a pattern like this, a pattern starts to emerge, right? And then what can you do? Well, if you know that this is based on a message or a paragraph or a book or something, you can start to say, okay, well, the most common letter in the alphabet is E. And I'm seeing this pattern, 101, occurring with this frequency. And by the way, that frequency matches the well-known frequency of the letter E in language. Do you see where I'm going with that? So then from that, you can infer that is likely to be an E. Was that sort of your question?
By that point, you'll know what the key is.
By that point, you know, getting the key is harder, but you start to break the security of the algorithm. So you may not, you know, I can't give you a recipe to like find the key magically, right? I don't know that trick. But cryptanalytics is this. You start here, and you start from here, you can see that what I can say is that this cipher is not 100% secure. It's not as secure as the one-time pad, for instance. Why? Because we couldn't, if we had used, now hopefully you understand that if you took this as the whole message, as one block, and I gave it a key that was as long as that message, and it was a random sequence of bits, what would happen? That you wouldn't be able to decipher it. But in this case, you are able to decipher it because you can do something like this. Do you see that? Does that make sense, guys? Any questions on this? This, by the way, is ECB. So this is actually the mode of operation that we saw before called ECB, or the electronic codebook, which is that what allowed us to see the circles and the squares, even though we had encrypted the image, because it retained the pattern and it was visually something that we could actually see. Think about that a little bit, right? So it's like, you know, let's imagine it as a picture, right? So it's a square. So what happened? Well, I'm encrypting and I'm going to use really large pixels here. Really large pixels. Okay. So these are the pixels, right? So why was I able to visualize this? Because this information, let's say that, you know, I'm just going to draw something very simple. It's like what is that if you had to imagine that as a shape? What is that? If that's a shape, it's a circle, right? Do you guys see that it's a circle? Do you agree with me that it's a circle? All right, great. So that's what we did in the ECB example. I just imagine all of this as just EXEER, right? Then I applied this key to each one of them individually, in a sense. So what happens? Even though I converted it to something else, right? Another set of numbers or whatever. So I'm going to use numbers here just to kind of simplify it. I can use another color, so let me do that. That's easier. I'm going to use red. So what did I do? I effectively converted these, let's say, all the zeros to twos consistently, for instance. And all the ones consistently, I converted them to what? To threes. Just for, you know, as an example here. Oops. But what happens, even though I converted them to another number, they're still all the same thing. And so the pattern remains. You guys see that? And that's why in the ECB example, we could still see the circles and the squares. And it's similar to this idea, right? It gets to the heart of what makes a secure cipher. Any questions? Is this making sense? Yeah? All right, so that's basically, you know, we're talking about what's a secure cipher. We've defined that the one-time pad, and we can go back to it, is secure. Is it this one? Yeah. So the one-time pad is secure, but because it's a random sequence of bits as long as the message, but unfortunately, that's not efficient. I've also shown you the other extreme of that, which is ECB, right? Where we we just have one key that is smaller, right? And then we break the message into blocks and we XOR the blocks. And I've shown you that even though that key was random, a pattern can start to emerge, as we saw here. And that's the electronic codebook. So we're looking at both extremes of that. And now we have to kind of start to, we obviously need to break our message into blocks. It's not possible because you need to have a key that's much shorter. But we need to start to think about better algorithms for solving this problem. Got it? So that's, you know, this is the justification for the next set of algorithms that we're going to be exploring. All right. Any questions or anything? That kind of wraps up this idea of the one-time pad and what makes a secure cipher. Okay, so I'll just do we'll do a little exercise. So, what time is it? It's 5:07. All right, so we're gonna do a pop quiz just to see how you guys process the material. I'm gonna give you a fun exercise. So take out a sheet of paper. I'm telling the truth here. So take out a sheet of paper, put your name on it, and I'll give you a problem. And yeah, I don't know that. Maybe somebody. Oh yeah. All right. So should be a fun exercise, right? Okay, so let's go ahead and it'll be multiple choice, so it's gonna be even easier than you think. And I'll give you some time to think about it. And the class is going to be a lot like that, like solving puzzles. All right. So this is a puzzle. So I gave you the example of the XOR operation, right? So you guys know how to do that. All right. So here we go. I'll write it here. Quiz. Okay. All right. It'll be multiple choice. So you are given a message M. So you have M. And you have its OTP encryption C. Okay. So if you have M and C, can you compute the key? That is the question. Okay. So you have M. So I'll say, so here, given M and C, can you compute K, which is the key, assuming the OTP cipher, which I've defined. Assuming the OTP cipher. Okay, I'll give you some time to think about that. I'm even going to help you out by making it multiple choice. I'm going to give you 4 choices. You need to select one, but you need to explain to me how you selected that one, right? So you need to give me like how you made that decision. So option A will be no. Okay. Option B is yes. Option C is I can only compute the bits of the bits, and D is yes. And the key is equal to M XOR M. Okay, so there you go. So given M and C, can you compute K, assuming the OTP cipher? And you have 4 choices. A is no, B is yes, C, I can only compute half the bits, and D, yes, the key is equal to M XOR M. All right, so take your time, right? We have plenty of time. And then once you're done, just give me the solution and put your name on it, bring it over here, and then we'll go over the solution once everyone's finished. So think about it. Yeah, please. Yeah, that would be great. Don't just say like, D, but actually give me some solution. So show your work, basically. This is where you would show your work of how you concluded, what you did. So just think about it. This will help you to really understand how this works. And so think about it a little bit. Yeah, you have to bring it up to me, yes. Once you finish, you can just bring up the sheet of paper with your name on it. But I use this for like the participation points. Remember, that's 10% of your grade. So you want to make sure you complete that. Thank you. Thank you. Is that everyone? Oh, yeah. So I have to, once I go over the solution, you can't submit your assignment anymore or your quiz, so make sure to finish, give you a couple more minutes, and then we'll go over the solution. Is that everyone? Okay, you're still working. It's fun, right? That's cryptography. Usually you're trying to break something, you're trying to figure out, right? Trying to find a pattern. So I think we're just waiting for one more person. Right, just one more. Are you still working on it? Or are you done? You are, yes. Yeah, your thoughts, yeah. Did everyone sign in? Thirty seconds. All right, great, thank you. All right, great. So that's everyone, right? So now we're gonna go over the solution. Okay, so which one is it? A, B, C, or D? So can you compute K, assuming the OTP cipher, if you have M and C? Yes, okay. So you're saying letter B. Okay. All right. Now prove it. So yeah. Yes, exactly. And you can show that would be show your work. You can actually prove it, right? So we'll do that right now. But yes, he's right. What's your name? Tyler. Yeah, Tyler's right. So B is the correct answer. Okay, that's the correct answer. Yes. The other ones are just to trick you. All right, so really it was yes. All right, so now let's look. So I'll go to a new page, okay? And we're gonna go over the solution. All right, so let's just say here's solution. The solution, right? Okay, so basically K is equal to M XOR C. That's your answer. Okay, so you can even do an example and prove it to yourself. You can like start with M, some bits, let's say 0, 0, 1, 1, 0, 1, 1, 1. And then the other thing we knew is the cipher, so C. So 1, 1, 0, 1, 1, 1, 0. All right, so then this would give you 1, 0, 1, 1, 0, 0, 1. And that's it. So you can basically, provide some kind of a proof like this that this would work. Oh, and I should say this is key. Sorry. Okay, and now you can take what the classic, so I just kind of like rearranged the terms to make it a little bit more confusing, but really what you would have done usually is you would take M and you would XOR it with K to obtain C. So if you take this K and you take this M, you should be able to show, right, that it'll give you this C over here. Does that make sense, guys? And you can prove to yourself that the answer is in fact. Does that make sense for everyone? Is that clear? Any questions on this example? Problem? All right, yeah, so that, it's meant to be like a fun exercise. And, we'll do little things like that throughout the semester to cover some of the topics of cryptography. So today, just kind of in summary, I'll go over what we, touch on the ideas that we discussed. So let me go over here. So we started with, right, SSL, right, the communication. So we have to share a secret key, and then we use that secret key to actually communicate, right? So then, SSL is going to be a difficult, a more complex topic, right, that will require us to go over many primitives, right? And today we started looking at these primitives, okay? So then, so I went here, and I basically started with one of the primitives, which is symmetric encryption, right? So forget about the key exchange for now. That's later in the semester. But assuming we've shared the secret key somehow, then we can start to encrypt, right? And the process is basically this one, okay? Like as I discussed. And so then that takes us to the XOR operation, which is this one, right? So that's the underlying operation that happens in cryptography because computers need to be fast, right? They're encrypting all the time, and computers are, manipulate bits, right? We have these operations, so that's actually what they can do, the fastest, basically. And then from there, we started to define, and this is really important, what is a cipher, right? So we talked about a cipher, a set of algorithms, E and D, where they meet these conditions, and then they have something called disequality constraint, okay? And this has to match all the time. And so from the cipher, then, we started to talk about what makes a secure cipher. So we started with the simplest example of the one-time pad, and that introduced randomness, right? And we saw that. And then basically from that, Claude Shannon tells us that this is a secure cipher. The definition of a secure cipher is where you have this relationship of the probabilities. Okay. And basically then we started to talk about why, you know, the one-time pad is not practical. So we have to start breaking, you know, using smaller keys, but that means we start to introduce patterns, right? Such as an ECB. And I explained this example here. So from here, I haven't introduced more complex algorithms, so we have to add, that's why we have to have algorithms. You see that? We had an operation, didn't quite work. So we have to start adding algorithms that will XOR these blocks, but in better ways, so that, you know, we meet that condition where there is no discernible pattern in our cipher. Okay, and then so finally we did the quiz to kind of introduce the topic. All right, so it's 5:30. All right, so I'll stay for a few minutes until 5:40. If you have any questions, I'm done with the lecture for today. The other thing I was going to do is go over the flipping one bit of the cipher, but I'm not going to have enough time for that today, so we'll do that on Thursday. All right, so on Thursday, we'll go over problem number 4 of the lab so that we can finish that homework assignment. And then with the rest of the time on Thursday, I'll just start doing a substitution cipher in pure Python from scratch, just to kind of get you guys to practice a little bit of Python. And that will be, yeah, the plan for Thursday, okay? All right, guys, so I'll stay for a few minutes if you have any questions. Otherwise, I will see you on Thursday.
Do you want to put these dots in the PDF?
Yeah, I need a PDF or a Word document. Yes, for sure.